Okay, hi everyone. Today we're going to work on integration again. But we're going to deal with exponentials. And that means we're going to deal with E and natural log, okay? E and natural log. And we're also going to deal with trig identities, right? Such as sine, cosine, secant squared, so on and so forth. Okay, stuff like that. But before we go into it, some of you guys that were asking me just to go over the mechanics of the power rule again. So let's go ahead and look at that. Our general rule is the integral of x to the n dx is x to the n plus 1 over n plus 1. So this usually works with polynomials. And the idea here is that we take whatever this constant value, whoops, not wrong one. We take whatever this value here is, and we just add 1 to the exponent. Because when we took the derivative of a regular problem, d over dx, of x to the n, this became n x to the n minus 1. Okay, x to the n minus 1. So we took the number and then we brought it to the front, and then we subtracted 1 from the exponent. Okay? So just to remind you, that's the original number, right? N is my original number here. Well, when we're in our integral, this is not the original number. This is the minus 1 version. That's why we have to add 1 back to it. And that's why instead of multiplying, we divide that original number back to it. So that's the mechanics of it. To go backwards, not only do we get rid of the multiplication by division, we add 1 because this n here is not my original n, it's my minus 1 version of it. To look at an example of this, d over dx of x to the 5 is 5x to the 4th power. Okay, x to the 4th. And if I take the integral of this guy, integral of 5x to the 4th, see, this is the subtract 1 version of it. So when I'm taking the integral, 5x to the 4 plus 1 over 4 plus 1, see how this is actually the 5? That's actually 5, right? Which is my original number. And this 5 gets rid of this 5 that we have brought down. Okay. So if we look at this as a weird fraction number, like a radical, let's take the integral of x to the 3 over 2.
Mr. Cole,
Yes?
you go a little bit up on your screen.
I'm sorry.
Thank you.
If I say x to the 3 over 2 dx, right? Where this is just my
At
n.
the 5x, would we add, would we also put the plus c or no?
Once we take the integral, yes, you would have to write a plus c at the end. So plus c at the end here, yes. Okay. And also back here I should write plus c, I'm sorry. For this is for indefinite integrals. I will talk about what a definite integral is a little bit later. Again, we're just starting off the year, working on something easy before we get into super conceptual. Okay, so for this problem here, we're going to add 1. So 3 over 2 plus 1. So x to the 3 over 2 plus 1, 3 over 2 plus 1. I'd rather just write 2 over 2, save myself some time. I knew it was going to be a fraction anyways. That's going to be 5 over 2 over 5 over 2 plus c. To rewrite that, we want to flip the fraction to be 2 over 5 x to the 5 over 2 plus c. Now, to go forward, if we take the derivative of this problem, d over dx of 2, I'm right 2 over 5 right in the front, and x to the 5 over 2 plus c. The exponent goes to the front, right, if I take the derivative. And doesn't that cancel out the 5 and the 2, essentially? We minus 1 from 5 over 2 becomes 3 over 2. And the derivative of a constant is 0. So we're back where we started from.
Wait, Mr. Cole.
Yes?
So why does the 2 go on the top next to the x?
So if you look at the fraction here, we don't like dividing fractions, so we multiply by the reciprocal instead.
Oh, alright.
Right. So if I want to write it as x over 1 over 5 over 2, this is x over 1 times 2 over 5.
Alright.
Yep. Good questions. This is like a lot of algebra too. The only calculus part here is adding 1, right? That's the only calculus part. The rest, rewriting it, it's really just algebra 2 stuff. Okay, so let's go through our new rules. So now here's a problem with our power rule, let's say. Here's a problem with our power rule. And if I give you the integral, so power rule is all great and dandy, except when we hit this problem, the integral of x to the -1 dx. Now, if I follow the power rule, okay, for this would become x to the -1 plus 1 over -1 plus 1. And I want you guys to notice something that's going to be problematic about this. You'll notice that you end up, sure, x to the 0, we know what that is, that's 1. But can we divide by 0?
No.
No. So this is where we're screwed. What happens is if we try doing the power rule to this -1 as exponent, when we follow the mechanics of our power rule, it turns out we end up dividing by 0. And this is not the way to solve this one. And if I write this a little differently, if I write instead integral of 1 over x dx, can you think of a derivative that when you take the derivative, the answer is d over dx of something, the answer is 1 over x. Do you guys remember the derivative of what gives you 1 over x as the answer?
Natural log.
You got it. Wow, there's almost like twins there. The natural log. Okay, and that's our identity going backwards. The power rule doesn't work when it's a -1 exponent. So we have another rule, which is our natural log. And the reason why is because when we took the derivative of natural log, that gave us our 1 over x. Okay, so let's go ahead and practice this. And we have a special identity for this, so just be aware that this one is slightly different. So the integral of 1 over x dx is natural log absolute value of x plus c. Now the absolute value is required. We can get rid of the absolute value sometimes if we can guarantee that the x values will always be positive. Like here's a weird example. If I say example, x is always greater than 0, then we can write ln absolute value of x plus c as just ln of x. Oops.
Wait, why is it absolute value again? Sorry.
It's our definition. I'll show you guys in a picture real quick why. Okay. The thing is, we cannot take logs of negative numbers. Let me go ahead and give you the easy one. Log base 2 of 8. What is log base 2 of 8? What log solve for exponents? So what is the exponent of 2 that gives you 8? The answer is
3.
3, right? Easy peasy. Right? Log base 2 of 16 is 4. Log solve for exponents. Log base 2 of -4. Is there an exponent of positive 2 that will give me -4? And not possible. So what happens is, the reason why the absolute value here is built in is that you cannot plug in a negative value to it. Okay? So we're only accepting positive values here for x. And you might start off with a graph. If I do give you the graph, we had just looked at it just a moment ago. If I give you a graph of 1 over x, the graph of 1 over x can be positive or negative, right? So if I did plug in a negative value here for x, it would have broke the equation. So instead what we do is we just say its absolute value right now. Okay. Also, what values don't work? Naturally, 0 doesn't work. X doesn't work. X can't be 0 here, as well as naturally x cannot be 0 here either. Let me ask you a question here. If I use log base 2 of 0, is there a number 2 times 2 times 2 times 2? Would that ever become 0? No. So they don't say x can't be 0 because it can't be 0 here already. But x could be -1, but x can't be negative 1 here, it would have died. So that's why we put the absolute value to protect ourselves. Okay. So let's look at some problems here. These are some easy ones. So before we go into chain on U-substitution, which is our chain rule idea, okay? If I give you a problem that says natural log of 2x, okay? If I actually take the derivative of natural log of 2x, we would say it's 1 over 2x times 2. Would you guys agree with this? Go ahead and take a look. The derivative of natural log of 2x gives us 1 over 2x, copy the inside, and then we chain rule it. So we are not doing these problems. We're not going to take, so right now, as of this lesson, we'll probably do it on the next lesson, but we are not going to, not doing the integral of 1, these divide out, right? Oh wait, whatever. Darn it. Okay, there's a reason why, okay, whatever. But we're not doing something like this. We're not going to do this yet. Okay, this one we can do, because this is just a 1/2 in the front. Okay, but the idea is that we're not going to have like something like, oh gosh, let me write this a different way. We're not doing problems like, we're not doing problems like this yet. Okay, this will be a U-substitution problem.
So we're not doing problems with chain rule yet?
Not yet. Just like when we first started, we didn't do any chain rule problems. We just learned the basic idea. So we were good with the basics, and then we were able to apply chain rule afterwards. So all these are super basic integrals. We're just learning the fundamentals of it. So if I take the integral of 1 over 3x, okay, right, dx, I'm going to say this. This is the same as the integral of 1 over 3, 1 over x, dx. Are you guys okay with me rewriting this? Okay, we have a constant 1 over 3. Same thing for derivatives. Integrals work the same way. If it's a constant, we can kick it out. So this is really the problem of 1 over 3, the integral of 1 over x dx, which leads us to become 1 over 3 natural log absolute value of x plus c. Straight definition. So for the most part, our derivative rules also work for our integral rules. So let's come up with a couple of them that we talked about when it came to derivatives. So here's the derivative rule. And then here's our integral rule, okay? So if I say the derivative of a constant times a function, this became a constant times the derivative of our function. Example, 3x squared, the derivative of 3x squared was just 3 times the derivative of x squared. And you would just have said 3 times 2x. The integral version of this is very similar to it. If I say the integral of 3x dx, this is the same as 3 integral of x dx, which is 3 times x squared over 2 plus c. Now, are you guys okay that this here, that plus c, is part of it? Now, here's something I need to bring up. It's 3 times x squared over 2 and c. So if I distribute this nicely, it will be 3x squared over 2 plus 3c. Now, you could write 3c, but here is a gimmick. We don't write that. We just write 3x squared over 2 plus c. Now, why do we write just plus c? It's because I never told you what that constant was going to be. So what is a random, not random, what is a constant times 3? It's just another constant. So we usually just fill in the blank at the end by just saying plus c. But if you want to do show the workout, 3c is just another constant, c. Is this c here the same as this c here? Nope. 3c, I'm calling it 3c1, is not the same as c, but it's just a constant anyways. Okay, so we can move constants out. Let's do another one. Okay, no, I think that was a good one. Okay. Oh, another one actually. Here, let's do another one. D over dx of, let's do 3x squared plus 2x. Okay. When I give you a problem like this, a polynomial, we treat this as two separate polynomials, two separate problems instead. 3x squared plus d over dx of 2x. Would you guys be okay with that? To say when we take the derivative of a polynomial or a problem with a plus sign in between, we actually just treat them as two separate problems. The integral version is exactly the same idea. If I take the integral of 3x squared plus 2x dx, we are actually taking the integral of them separately. So the rule allows us to split our integrals if we find that's going to be easier. So a problem that we could do, for instance, right now is, well, this one's just the case study. But here we go. If I say let's do 32x to the, let's do 7th plus 1 over x dx. The first problem when we take the integral would be the integral of, nope, sorry, not integral, we're done, equals to 32 x to the 8 over 8 plus natural log of x plus c. Okay, that's what you would write. This is our easy way. We would write it. But what would this actually look like if I took all the steps involved? Now, all the steps involved, of course, take a lot of writing. But I would have broken this up as integral of 32 x to the 7 dx plus the integral of 1 over x dx. Okay? We take the integral of this, so it would be equal to 32 x to the 8 over 8 plus c. I'm going to call that c1 plus the integral, sorry, not integral, I keep doing that, natural log absolute value of x plus c2. Because these constants are not the same, but here's something that we make it easier for ourselves and everyone else. Instead of writing a bunch of c's at the end, c1, c2, c3, c4, we say, hey, isn't c1 plus some c2, some constant plus some isn't some constant plus some constant just another constant? And we'll just label that as some generic c. So that's why for indefinite integrals, we just have to write plus c at the end, and that plus c covers all the possible constants added together. Because it's just some constant. There's some change. If I add some change in my right pocket with some change on my left pocket, I still have a bunch of change in my pockets. Okay. Now, this dilemma, this natural log only happens when it's x to the 1 power on the bottom, x to the -1 on top. Okay, so if this only happens when you have x to the -1 on top or 1 over x. That's when we end up with natural log. Okay. Now we'll learn later, if the problem gets a little more interesting, if I say 1 over x plus 3, this will actually be the integral of this, will be natural log of x plus 3. Right, and that's something that we'll learn later using our U-Substitution. But FYI, just in case if I write this instead, this will be, you can probably guess it, what is it going to be? But this is slightly wrong. We also need to include that. It's because this is a U-sub problem. These are U-sub problems. Okay, they don't fit our identity exactly, and we would have to learn something about U-sub for it. Now, just to prove the point to you guys right here, just to prove the point to you guys, I'm going to rewrite this as 1/2 natural log 2x plus 5. Okay, plus c. I'm going to get rid of the absolute value here. 1/2 natural log of 2x plus 5. And then if I take the derivative of this, this becomes 1/2. Derivative of natural log is 1 over 2x plus 5. Chain rule times 2 plus 0. This becomes 1 over 2x plus 5, which comes back to where we started from. And that's something where we're going to learn later when it comes to this U-substitution. The fundamental rule is 1 over something. That's natural log of something. 1 over something, the integral of 1 over something, 1 over something is natural log of that something. Okay, so natural logs seem super complicated, but they're actually not. We just have to be able to identify when we have natural log. Okay, let's do our next easy integral. So the next easy integral is exponential. So here's the easy one. What is the derivative of e to the x? Whoops, I don't know why I wrote that. What's the derivative of e to the x? Just e to the x. So is the integral of e to the x. Okay, the derivative of e to the x is just e to the x, and the integral of e to the x is e to the x. So let's add this to an example. The integral of 5 e to the x. Well, this doesn't match my identity. Well, we could get rid of the 5, can't we? That's a constant. So this would be 5 integral of e to the x. And we know what derivative of e to the x is just 5 e to the x. Don't forget to add a plus c, since it's an indefinite integral. That's it for ease, really. Now, we'll talk about U-substitution later, but let's do another problem just because. 1 e to the x over 2. That's a 1/2 in the front. And then the integral of e to the x is back to e to the x. Easy peasy. And the reason why, again, is because the derivative of e to the x is e to the x. Now, what if it wasn't e? What if it wasn't 2.7 blah, blah, blah? What if it was a number like 3? So let's go ahead and look at this review question. What's the derivative of 3 to the x? Okay, what is the derivative of 3 to the x? This was 3 to the x ln of 3. Do you guys remember that? 3 to the x ln of 3. So the derivative of an exponential is itself multiplied by the ln of the base number. The derivative of, let's do something like pi, right? Pi x. This is pi to the x ln of pi. Now, if you remember this rule, if I take the integral, does the integral undo everything we did in our derivative? It undoes everything we do in our derivative. So if I'm going to multiply by my base, the integral is going to not multiply, divide by that base. So if I take the integral of 3 to the x dx, this is like the integral of e to the x, okay? Because that's a constant value. This is going to be 3 to the x. But because the base isn't e, we'll find ln of 3. Reminder, ln of e cancels out to become 1. That's why their answer is just e to the x. In this case, ln of 3 doesn't cancel out, so we're stuck with ln of 3. Oh, wait. Messed up. Sorry. I wrote it wrong. I did the derivative. It's the other way. If I'm multiplying to divide, if I'm multiplying to take the derivative, I divide when I take the integral. Sorry, I wrote that wrong. I was thinking about the derivative again. Okay, so just as a FYI again, if I'm multiplying, when I take the derivative, we divide when we take the integral. That's really the rule, like no joke. Okay, so I'm going to take the derivative of this, d over dx of 3 to the x. I'm going to write a 1/3 natural log of 3 so you guys can see a little differently, plus c. Here's the FYI. 1 over natural log 3, that's a constant value. Isn't that just a constant? And what do we do with constants? We just write them in the front. And d over dx of 3 to the x plus c, some constant, is 1 over ln of 3 times 3 to the x ln of 3. And check it out. The natural logs cancel out, leaving me just 3 to the x, where we started from. So as a reminder, when we do take the derivative of exponentials, where my base is a constant number, we have to multiply by ln of 3 right here. So when I take the integral, we just have to write it as a division going backwards. Okay. Now, just to foreshadow, oh no, forget, we won't do foreshadowing, but we could, but we're not. But later we're going to have to take integrals of 3 to the, let's say 2x plus 1, something like this, okay? And this integral would be 1 over, it would be 3 to 2x plus 1 over natural log of 3. But then we're going to have to actually add a 2 here. Okay, and that's because of a chain rule. And like what we call U-sub.
Wait, why do you put it 2 again?
Let's go ahead and
I
take a
know
look
because
at
of chain rule, but
because of chain rule, yeah. So if I write 2x plus 1 over, and I'm going to write this in front. I'm going to write 1 over 2 natural log of 3, okay? I'm going to write that in front. Just move it in the front. If I take the derivative of this guy, right, let's move this out, 1 over 2 ln of 3 out. And we're just going to take the derivative like we traditionally would have back before winter break. Okay, so the derivative of 3 to the 2x plus 1 power is we take the derivative of the outside first, which is the 3. Okay, so 1 over 2 natural log of 3. What's the derivative of an exponential? It's just itself. 3, 2 to the x plus 1, ln of 3. Are you guys cool with that part? Followed by chain rule. What's the derivative of 2x plus 1? That would just be a 2. And then so these guys would cancel each other out, leaving me my original problem, 3, 2x plus 1. So we're going to have to worry about this. If it doesn't look exactly like my rule, we're going to have to what we call U-substitution later. And U-substitution is a pretty easy trick. Once we learn about it, it actually makes our life easier. Makes our lives easier.
Mr. Koba, I thought we were trying to get the original problem.
We are. From here to here. That's my original problem, to work backwards.
They're the same though.
Yeah, they're supposed to be.
No, but like, what's the? Oh, so the derivative or the first problem of 2x to the 1 or 2x plus 1
Mhm.
is what it equals, and then you just checked your work pretty much.
Right.
Oh,
So the idea
I
is,
was really lost. I'm sorry.
yeah, the basic idea is that if I take the derivative of an integral, okay, so look, this is the derivative of an integral. So they should cancel each other out. So we should be left with our original function at the end. Essentially, they're inverse operations of each other. Right? Okay. All right. So let's do. So we did pretty much most of our exponentials. Let's go into trig now. Here we go. Trig identities. Now, for the most part, all the basic ones work out. That's just how they work. Let's look at our identities. The derivative of sine is cosine. We know that. That was a super easy one. The derivative of, let's actually, of cosine. Whoops, darn it, I don't know why I wrote the equal signs there. Of cosine is negative sine. And the derivative of tangent is secant squared. The derivative of, let's say, cosecant, and the derivative of secant. You guys remember my dumb joke? The derivative of secant is secant tangent, excuse me. And the derivative of cosecant, all cos always give you a stupid negative. Whenever you take a derivative of a co, it's bad luck for everyone. Cosecant x, cotangent x. The derivative of a cotangent, oh, that's a co also, right? So that's going to be negative cosecant squared. Okay, so if we can go forward, we can go backwards. And the rules follow the same here. So let's go see if we can make a guess. The integral of, let's do cosine first, is the integral of sine is the integral, I forgot to write dx, I'm sorry. The integral of secant squared dx is, oh, that looks terrible. The integral of cosecant cotangent is the integral of secant tangent is, so the integral of cosecant squared is, okay. So if you want, you can take a look at the cheat sheet online, of course, but the only part you have to be careful of is if you know there's supposed to be a negative to begin with. So the integral of cosine is just sine. Now ask yourself why. Is the derivative of sine cosine? Yeah. Okay, the derivative of sine is cosine, so the derivative of cosine is back to sine. The derivative of cosine, though, is negative sine, right? So the derivative of cosine is negative sine. So to go backwards, the integral of sine is not just cosine, it's negative cosine plus c. Why is there a negative? Because the derivative of cosine would have been negative sine, so I'm just moving the negative back over. Are you guys catching that negative part? Okay. The integral of sine is not really sine, right? That's actually the derivative of cosine. It wasn't the derivative of cosine a negative value, so we have to stick a negative there. The integral of secant squared was really the derivative of tangent. So this is just tangent. Oops. Going backwards, ask yourself, what's the derivative of tangent? It is secant squared. No positive or negative. What's the integral of cosecant cotangent? Well, this was cosecant cosecant. But don't forget, there was a negative because cos always get that negative. Stupid cos. Secant tangent was secant, no negative. And cosecant squared was cotangent. But yes, that one had a negative. Okay, so how does this work in play? So pretty much if you see the integral of a trig function, okay, you have to go back and say, hey, what trig function gave me that identity? Now these are just the basic ones. These are not the ones that we have to derive or play around with. These are just, if you see it, this is the identity. If I see secant tangent, okay, what did I take the derivative to get secant tangent? Well, that was secant.
Mr.
Yes.
For a cosecant wait, CSC cot x, why isn't that a negative? Like in the front.
Do you mean this one here?
Yeah.
Cosecant? You're right. The negative, though, as I write on the other side, the equal side, because the original problem did not have a negative, the integral of that will have a negative.
Okay.
So, because if I take the derivative of cosecant, it's cosecant cotangent, but then I'm going to include that negative to make it a positive going forward. Let me go ahead and show you the example of that. If I take the derivative of negative cosecant x, okay, this would give me negative cosecant cotangent, and the negatives will become a positive, so we end up with positive cosecant cotangent. Okay, so when I take the integral of this, positive cosecant cotangent, we end up with a negative sign, and then cosecant x. There has to be a negative for these cosecants. All these cos get a negative. That's why the integral of sine isn't just cosine. That's because you're thinking about the derivative. So I need a negative there because it was going to give me a negative value. So let's highlight the ones with all with negative. All these guys here are negatives because all their derivatives were negatives to begin with. The derivative of cotangent gives me negative cosecant squared, but there's no negative here, right? See, there's no negative here. So that's why we have to write it over here, because negative becomes a positive. We had to have the negative here, so it would be positive here. Okay, so what if I change this problem over here? The integral of 3 secant x tangent x dx, okay? Well, since 3 is a constant multiple, that's just 3 secant x plus c. Because the derivative of secant is secant tangent. Okay. What else is there? If I give you the integral of negative cosecant squared x, hey, the negative's here already, isn't it? But let's rewrite it as just stick the negative on the outside. That's negative. The integral of cosecant, cosecant, yeah, is cotangent. So it's going to be negative cotangent, not squared, just cotangent x plus c. And then this is going to be just positive cotangent. Or you could have said that was the straight identity. All right, that's it.